All right, today we're going to start section 2, and we're going to continue on with what we've been doing with ratios and expand it to talk about rates, and especially unit rates. Now you definitely want a calculator, so make sure you've got that, even as we do our notes today. And the other thing is get out a piece of paper and get this heading up here, because at the end of today I'm going to check and make sure you have both your 5-1 notes and your 5-2 notes. Okie dokie. Awesome. All right, here we go. So the first thing we have to talk about is, okay, what is a rate? See, yesterday we talked about a ratio. A ratio, again, is just a fraction comparing two numbers. So what's different about a rate? Well, here's what a rate is. It's a fraction, but it has different units associated with it. Okay, so I'll give you a second to write that down. And then these are much more common than you actually realize. Okay, let's see. When you buy a car, you're really wondering how many miles per gallon of gas that car gets, because that fuel efficiency is an important thing. When you are exercising, you might focus in on your heart rate, and that's where you're counting how many heartbeats you have per minute and that sort of thing. Okay. When you're resting or when you go into the doctor, they usually check your pulse and they'll analyze that. And so if you have something like a heart rate of, say, 70 beats per 1 minute or 60 beats, that's a normal resting heartbeat. Okay. So that's what a rate is. And in fact, let's go back to this driving one about miles per gallon. Let's just say, oh, when I go to drive home to see my parents, it's 220 miles, and sometimes I can do that in about, on a good trip, maybe 11 gallons of gas. All right, so that's a rate. I have miles on the top, gallons on the bottom. Units are different. Now, what is a unit rate? Well, a unit rate is a rate, just like this, meaning I've different labels, but the key here is that your denominator is 1. So here's a great example of a unit rate. 70 heartbeats in 1 minute. My denominator has a number of 1. That's a unit rate. If I go to simplify this rate, when I was doing my mileage in my minivan, that would simplify to be something like 20 miles per 1 gallon. That's called a unit rate because the denominator's 1. All right, so let's see how this works. Okay, first example. Penelope is a speedy typer on the computer, or a typist, and she can type 90 words in 2 minutes. How many words can she type in 1 minute? I want you to think of this as a fraction. And now it's important to include the labels all the time. 90 words over 2 minutes. Now, to simplify this or to get the unit rate, we want to figure out how much is that in 1 minute. Now, a couple ways you can attack this. Okay, this is kind of like a proportion, so you could try and solve it that way and try and get your cross products equal. Or if you look at 90 over 2 and grab your calculator and simply take 90 divided by 2, because that's the number part of this fraction, you'd get exactly 45. 45 over 1. 45 words per minute. Today is going to be really important that you include your labels. All right, let's talk about hockey. I'm praying that the Wild are going to finally get better here. But last season, so this was the 2013-2014 season, I looked up Koivu's stats, and Koivu had 54 points last season, and he played 65 games last season. So I'm asking, what is the rate of Koivu's points per game? Hey, here's a hint right there. The per word is usually where your fraction bar goes. So you know that the points, since that came first, is going to be your numerator. Game is going to be the denominator. Let's see, 54 points, 65 games. Now right away you're looking at this and saying, hey, Miss Best, this is not going to be a number bigger than 1. And that's correct. And frankly, that statistic makes sense to me because every hockey player doesn't necessarily score a point a game. If this was basketball, that'd be a different story, but this is hockey. So go ahead and grab your calculator, all right? And what you're going to do is take 54 divided by 65. That's probably going to give you some nasty old decimal. And we're going to have to kind of round it off a little bit because we want to talk about how many points is that per one game, and that's why we're dividing. All right, well, when I look at my calculator, if I said let's round to the 10th place, I get around 0.8 points per game. He's almost getting a goal a game or an assist a game, which is pretty darn good, frankly. And that was last season. All right, let's look at another example, okay? On this one, ooh, here's ones with huge, huge numbers. All right, this is a huge one. The population of the United States is about 300 million. There are 435 members in the House of Representatives and Congress. So what would be the rate of the population, in other words, the people? So I'm going to change this actually to think about the population. This is people. How many people per representative? Okay? People per rep. So we have to put 300 million on the numerator of our fraction. And we're going to put 435 in the denominator. Right now, I am really saying thank you to the guy that invented the calculator. So, grab yours, plug in 300 million. That's kind of hard to do. You got a lot of zeros there, 8 of them. Okay? Divided by 435. This is going to be a pretty ugly number, so get ready here. For one representative. And let's round this to the nearest whole number because frankly, if we're talking about people, gross, I don't want to talk about fractions of people. So this is the number I get. 689,655, and then I have a decimal 0.1 something. Since that's a 0.1, I'm going to round down and just leave it as 655. So approximately 689,655 people are represented by one representative in the House out in Washington, D.C. Interesting. Okay, here are some that you should use just to estimate. So I'm going to say, hey, put that calculator down and let's estimate each of these. That means you're going to round, okay? Now, right now, if you have 468 students to 91 computers, okay, oh, this is kind of gross. I look at this and I think, well, 91, that's pretty close to 90, okay? And then when I look at the top number, I'm like, ugh. I wonder what's a good number that works with 90 that I could round this to. Because, you know, initially you might think like 470, 475, but I'm thinking, I can't round that or divide 90 into there easily in my head. But if I instead thought of, hey, you know, in my 9 row on the multiplication chart, 9, 18, 27, 36, 45. Whoa, 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 stop right there. Because I have 90, that's kind of like 9. I can think of all of these numbers with zeros after it. I'm going to round this to 450, just because this is a number that's compatible with this one. So there's about 450 students per 90 computers, and that would be a 5-to-1 relationship. So there's around 5 students per computer. That would be an estimate. Now, is that perfectly accurate? Of course not. If I wanted to be perfectly accurate, I'd grab a calculator and do it. But I want you to be able to look at it and get an idea in your head as to what it should be close to. All right, what about this one? Estimate 313 feet in 8 seconds. 313 in 8. Well, let's think about this. You could do this a couple different ways. Like one way, I might think of this as I'd leave the 8 seconds the way it is because I know that 8 goes into 32 perfectly, and I'd simply make this a 320. So I'd round 313 up to 320, and I could think, hey, so that would be around 40 feet per second. Or some people might say, gosh, I want to take that 8 seconds and round it up to 10. And then this one, well, you could probably leave it where it's at, or if you wanted to round it up to 320 maybe, then you'd get around 320 feet per second. In 1 second. You know, we're estimating, so you're going to get some variation in the answers depending on how you rounded. Okay, this one's a little more accurate because we didn't mess with the 8 at all. But I could see where you would get an answer like, oops, not 320, sorry, 32 feet per second. I could see where you'd get an estimate like this, certainly, and you just have to show me how you're rounding so I can gauge how good your estimate is, okay? All right, let's jump to what I love to do, and that's when you go shopping. Have you ever gone to Sam's Club or any of those Costco, any of those warehouse places, and they'll have the products in the bigger packaging? Actually, you can see this when you go to the grocery store, or if you go to Target. You'll see that they'll have smaller things of peanut butter, larger containers of peanut butter, and you're trying to figure out what's the best buy. Okay? Just because it's a bigger can, does that always mean it's the best buy? Well, we'll have to see. $2.60 for 2 pounds. Go ahead and calculate the unit rate here, which means take 260 divided by 2 so that we're calculating the cost for 1 pound. This gives you $1.30. Okay, so that's the price per pound if I buy this jar. What happens if I buy this big old can? Take $6.54 and divide it by 5 pounds. Make sure you leave your labels in your answer, okay? So this is going to be dollars. This is going to be now for 1 pound. Grab your calculator and take 6.54 and divide it by 5. And I think, as I'm grabbing mine here because I want to make sure I'm accurate, I end up with 1.308. Now, I know I'm talking about money. This actually went to the thousands place. Compare that to this one, $1.30 to $1.308. Which one's the best buy? Actually, this smaller can is the best buy. Not by very much. It's only just this little part of a penny here. But contrary to what you think, the smaller can is a better buy, or the smaller jar. All right, so let's talk about soda. All right. Sometimes you think buying that 20-ounce bottle is a good deal, so you're spending $1.50 for 20 ounces. Let's just see how much you're paying per ounce. $1.50 for 20 ounces. So on that single bottle, find the unit rate, which means take $1.50 divided by 20, and I think you end up with, let's see, 1.5 divided by 20. You end up with this is a dollar sign, 0.075. So really like 7.5 cents per ounce. Now, does that sound bad? Oh, I don't really know. Let's see what happens if you buy a 6-pack. Wow, this is an expensive 6-pack. Yikes. $5.04 over. Let's see here. That means there's like 6 of, I don't know, these cans. But I was figuring it out per ounce, so we should really figure out how many ounces do you have. Let's see, if each can is 12 ounces and you've got 6 cans, that means you're buying a total of 72 ounces here, okay? All right. So now go ahead and let's calculate what your unit rate is in this situation. We're going to divide by 72. All right, and this one, amazingly, it's pretty darn close. You end up with 0.07 or just 7 cents an ounce. Actually, I'm guessing a 6-pack is way cheaper than that. I just tried to make these examples close so that you could see which is which. All right, so that little 20-ounce bottle, you're actually paying more for the Mountain Dew than if you are buying a whole 6-pack. Now, do you need the whole 6-pack? Maybe not, but just realize from a unit rate standpoint, you're paying more per ounce for that Mountain Dew in the 20-ounce bottle. This is really the best buy, the 6-pack. Alrighty, well, here we are. This is what I want you to start working on now for tomorrow. Or actually, let's see, it'll be the next time I see you because you have a little bit of a long weekend. So, in your workbook, and I forget off the top of my head what page this is, but find 5-2 in your workbook. Use a calculator. Make sure that you are labeling absolutely everything that you have these rates on, okay? It looks like this is page 33. All right, so let me write that up here. Page 33. Again, make sure you're labeling things and go from there. Good luck.